Hello everyone. So today I'll be talking about fine-tuning large models with LoRA. That's low rank adaptation. First a bit about myself quickly. Soumendra, so I think he pretty much covered the whole thing. If you want to connect to me on Twitter, that's Data Biryani. And thanks to Aditya, Nirant and Lalit for helping me prepare for this talk and providing feedback and other assistance and their Twitter handles in case you want to follow them. Great people. Right. So before we dive into other things, let's first look at why are we talking about LoRa, like why do we care? Right. So the important thing is that when you are taking a small model, let's say ResNet 50 and trying to fine tune it, it's kind of, you don't need to care about these kind of things, right? Those are small models by today's standards and pretty much you can throw them on really low powered GPUs and fine tune them for hundreds of tasks that you might have in mind, right? All of that really changes when you come to really large models, and that's what LoRa is about. But before going deeper diving into LoRa, sorry, let me talk a bit more about LoRa quickly. Right, so fine tuning for multiple tasks, that's why we care about LoRa, because we can really do it for very large foundational models. And second, it's proven in practice, right? If you look at any large language model today or transformer based vision models like stable diffusion, a lot of the fine tuned models you'll find they come as LoRa patches, right? Really small models, but they really work very well for specific tasks. You need very less amount of compute to train these models as well, and still they perform almost as well as full fine tuning. If you were to fine tune the entire model, they would the performance from LoRa is still comparable to that. And lastly, and this is fairly important, you can so you basically share your fine tuned model as small patches, right? Very small files. So your original model could be 8 GB, but you could be sharing a file that is like 30 MB or 80 MB, which completely captures the fine tuning that you have done for a given task. Right. So that's why we are talking about LoRa, and right. So and here's a quick agenda. So we'll first spend some time understanding what fine tuning is, review the classical view of full fine tuning quickly, and then look at the kind of issues that come from there, right? Like why does it not work well for larger models? And then we will look at different kind of strategies that you can employ to fix the situation, LoRa being one of them. Then we will quickly look at the ideas behind LoRa in LoRa distilled. We will do a small deep dive into the mathematics behind it, and then quickly cover a few things you should look at if you want to go further down into LoRa. Right, so let me first do a very quick review of what does the machine learning training and fine tuning process looks like. So this is the full picture, and we'll refine it and focus on the parts that we really want to talk about, right? So you get some input, which is you have some features, you have some ground truth, you feed that to the model, and the model generates predictions. You compare that to with the ground truth, you look at the loss, combine it with the optimizer, and through backpropagation you get some model weight updates. And then you combine this model, the model weights that currently exist, combine them with the updates, and you come up with the model with the updated weights that you are going to use in the next iteration again, right? We do this batch by batch, epoch by epoch. Right. So simplifying this a bit further, what we really have is that we have an input matrix X for this round, and we have the network weights from the last round, and to get this we need to add the weights from the last round and the updates from the last round, and that is the network weights we have after last round of training. And then in this round of training we get some updates, and then we combine the two and we are ready for the next round. So simplifying that a little further, so I'm doing this because I'm going to use this to describe how LoRa works. right? So I'm spending some time doing this. So the same view, so we get the input matrix x, x prime, this round, and so then we need two things. We need the network weights that are going to be used in this round of training, and then we produce weight updates. And some stuff happens, so we from w prime we get delta w prime, and then we produce the network weights for the next stop, which is basically, and we add them up and we are ready for the next round. Right. So while training, it's fairly straightforward. We are training the entire network, right? But then comes fine tuning. So how many of you do not know what fine tuning means? Model fine tuning. Okay. So quickly, so let's say you have trained a really large foundational model for image classification task, which classifies a given image into 1,000 classes. But what you are really interested is in classifying between breeds of dogs. So instead of training another model from scratch, you will train, so you'll take that original model and retrain it, fine tune it on a really small data set, which basically is of dogs belonging to different breeds, and do a lightweight training, a lightweight update of the network parameters, and that's what we call fine tuning. Right. So three standard approaches depending on how much of fine tuning data you have, and right. So one is that you keep the entire model frozen. Sorry, you keep the entire model frozen, and you simply put a classifier on top of it, right? So you treat the numbers coming out of the model as features, and you build and you train a classifier on top of it, or you put a few fully connected layers in front of it, and discard whatever fully connected layers were there, and you add your own. You keep the model itself frozen, and you fine tune this part, or you can simply update all layers, which you won't really do. You will keep this frozen first. Otherwise, if you completely unfreeze everything, all these weights are destroyed, right? So you do fine tuning 1 a bit, and then you do fine tuning 2, right? So if you have this entire network, this is your pre-trained network, let's say. So you could take out that final classification head, which classifies between 1,000 different classes, and maybe put something that classifies between 128 dog breeds, right? And instead of training the entire network, you typically want to keep a large part of it frozen, because you typically don't have enough data to fine tune all of that. And one thing we understand about this is that the features that the network is learning is hierarchical in nature. All the low level features will be learned first, all the high level features will be learned later on, right? And depending on how you feel about it, you might want to further unfreeze other parts and freeze only a small part of the network. So this is what we have been doing. We have been experimenting around this, trying to figure out what works best, what to freeze, what to unfreeze, right? So now, what are the problems with that? So the first thing is that before I talk about anything else, I would talk about blind tuning, right? So you have these features, which are like all these layers are being produced by a set of features, right? Filters, which we call features, right? So there are a hierarchical representation, but you don't know beforehand which feature is going to be useful for what. I mean, you talk about a simple setting where you are trying to classify between breeds of dogs. You probably don't need to think very deep about it. But if you look at a large language model like GPT, there are like a lot of concepts which are distributed over the entire network, right? And if you freeze all of those previous layers and unfreeze only the last few layers, so you are not necessarily tuning the things that you really want to tune, the features that you want to really tune with for your data, you are locked out from them, right? So it might be about introducing a new concept or it might be realigning a new concept, an existing concept, right? If you want to realign an existing concept, for example, you can imagine that freezing most of the network is fine. You just need to work on the last few layers to realign concepts. But if you are introducing new concepts, you know that you need to fine tune some features from the previous parts of it, but all of which are now frozen and you can't access them. I mean, you could, but that requires a lot of compute and, more importantly, a lot of data that you do not necessarily have. Right? And so that's what blind tuning is about, multitask fine tuning. So in practice, you probably haven't even noticed it, right? So you want to build, let's say, 100 different classification models. The thing is, you are doing that training for 100 different models, which is really going to add up when you have a large model, and honestly it's not even really that feasible, right? So you could ask, what if we have the same backbone and we simply attach heads, right? A multitask head to that. So the thing is, you train that model once, but there is no way you can add another task to that multitask head, right? Because you could freeze a lot of things, do your training, but you have no guarantee that the new training regime that you are going through will not destroy the features that have been learnt for the previous tasks. So when you try to learn multiple tasks with the same model, that becomes an issue, and that directly leads to compute and data, right? You are refining the same feature set again and again, and there is a lot of commonality to the tasks you are doing, and you are wasting your compute and data resources on that. So what it boils down to is that the compute and performance trade-off is a bad one. So we are locked out of this feature space. We can only blindly take some parts of it, try to fine tune that, but the amount of compute we have to spend to get a good performance, that trade-off is a bad one, and that's what we would like to optimize. Right. So I've talked about a few of the things that are wrong with the full fine tuning. So now let's look about what the ideal case is. What are the kind of problems we want to solve when we try to improve upon the full fine tuning that we can solve with more techniques. Alright, so I'm going to introduce 7 principles, and we'll see how each of them, why we care about each of these. So the thing is, so this is one of the older principles in classical machine learning, right? We talk about the parsimonies of parameters there too, right? If you have very few independent variables, that's a better model than a model with a lot more variables, right? So here we care about the number of trainable parameters. We want to minimize that as much as possible, and that's typically going to lead to a better model and a more stable model, which will also require a lot less compute. More importantly, this works really well when we need to optimize a lot of different tasks. Sorry. So that directly leads to computational efficiency, of course, but I would like to keep that separate, because we do care having less number of parameters, because that is with Occam's razor, that is generally a good thing, will lead to more stable models. So instead of talking about robustness of models, I decided to include computational efficiency, because that is something that we care about more. And of course, so we also want near equivalence with full fine tuning, right? Assuming you had all the resources, the kind of performance you could get from that model, we should be able to match or like almost match that that kind of performance, right? Otherwise, it's trivial to throw a lot of performance for less compute requirement. That is not very interesting. And lastly, we want task invariance. So this is not lastly, this is just number 4. So we shouldn't have to fine tune the architecture also for fine tuning for the task, right? So if you remember, if you have done this kind of fine tuning in computer vision specifically, right, you don't know how much to freeze, how much to unfreeze, depends on your task entirely, how difficult it is, how many categories are there in your task, right? So lots of papers on like how many layers you should freeze, unfreeze, and what kind of schedule should you follow, right? So there's a lot of work around that, and plus we also look at, I mean, we are tuning this architecture, like how many neurons should be in this fully connected layer, right? So those kind of things, they become task specific. We want to be able to come up with a approach, at least ideally, that lets us tune the exact same thing all the time, right? And now two more things that are really important, and this is what is missing in the full fine tuning particularly. So I'm going to talk about isolation and localization. All right, the parameters that are fine tuned should be distinct and separated from the rest, right? So that when you're fine tuning a set of parameters, it does not significantly change the rest of the network, right? It's not, we don't want to do full fine tuning, right? We are minimizing our full fine tuning, which means we are not updating a lot of parameters. So we want to isolate the parameters we are actually training so that they don't destabilize the rest of the parameter space, because then we can take this model and train it on 10 different tasks, and you know, things, a model that has been trained for task A can now be trained for task B, because the effects of training for task A is now isolated, right? So you don't have to again start by training from scratch, right? So it helps maintain the stability of the model, as I talked about. Okay, so the whole thing is long form description of basically what I am saying. One thing I would like to point out is that we care about catastrophic forgetting. The example I gave earlier was about multitask fine tuning, right? You train for task 1 and then it's easier to train for task 2. But another thing that happens is that when you are training this, you are training from different parts of the network, and you are changing the parameters that were trained on the full task, the generalized task. So there is general knowledge that is contained inside the model, and when you fine tune a lot, if you are changing a lot of those parameters and the parameters you are training are not isolated, then it might start to forget the general knowledge that it had learnt, right? That's what we refer to as catastrophic forgetting, and that is something we want to avoid, and isolation will do that. And the localization is the parameters that we want to fine tune. We want them to be concentrated in a specific region or a layer, right? Something that we can reason through. So this is important for two reasons. One is that this leads to more interpretability, more transparency. You understand what is happening in the fine tuning process in the entire model, but more importantly, you can now localize, you can also localize all the changes that is happening to the model to that very specific parts, right? Now this can be like a central architecture, and in every fine tuning task that you perform, every new model can basically become a plugin to this centralized architecture, right? So basically that interpretability and efficiency, right? So as I mentioned earlier, model patching becomes possible. You are not replacing, you are not like, to fine tune an 8 GB model, you are not coming up with another 8 GB model, you are coming up with a patch which is maybe 80 MB in size, and you are sharing that with others. And if you are from the diffusion community for images, you have probably seen this in action a lot. So people are like, most of the models that people share around, they are like either textual inversion, Dreambooth or LoRA. Right, so I'm going to go through this very quickly. So a metaphor, just trying to understand this as a metaphor. So let's say you are a painter, you are creating a painting, and then you need to adapt the painting for different purposes. So what does isolation and localization look like in that context? So broad strokes, you have painted, that's your pre-training. Now you need to add finer details, right? and you have like, let's say 100 different copies of the same painting, and you need to produce different effects. So how can you make those changes? So isolation is like making sure your fine touches don't mess up your broad strokes. That's the principle. Like you are going to do fine touches, they should not mess up the image. And localization is that you're not applying your changes everywhere. You're applying it only a few places. Right. So what does that look like? So let's say you want to change the setting from daytime to nighttime. So instead of having to paint everything everywhere, you could paint in a single corner, painting the night sky and painting a moon on it, and that would be localization. Right. And isolation is to perform those tasks. You are changing only specific aspects of it, right? So okay, I'm just going to. I've mostly talked about this, but I'm going to speed through this because I think I'll not have enough time for the maths part when we get into it. Right. So I talked about isolation and localization, and I think this is the last one. So which is conservation of general knowledge. So that's one of the good benefits that we get from isolation, localization, those kind of principles, parsimony of trainable parameters. But we do want to explicitly do this and verify this, right? When we are fine tuning for a specific task, we want to conserve the general knowledge, ensure that it remembers what it was originally trained on, and this is what parameter efficient fine tuning is about. Like tons of papers in the space, and you can look at those papers and they will talk different versions of these same underlying principles, which typically motivates how they go about coming up with new algorithms for parameter efficient fine tuning. So how does full fine tuning perform in each of these aspects? Parameter parsimony is literally the worst it could be. Computational efficiency again is the worst possible solution for that. This is the best solution for near equivalence with the full fine tuning, but that's not very interesting. And task invariance, again, it's pretty bad at that. Isolation, localization, it's like the theoretical worst algorithm that you could design for doing this. That's full fine tuning, but it is of course like it's by design, right? We are benchmarking everything against that. So it's the worst possible solution, and we want to do better than that. Right. So just summarizing what I've been saying so far. Small models, full fine tuning is great. Your models are large, you want to look elsewhere. Right. So now let's think about how we can improve fine tuning. We'll talk about 3 different ideas and see how they make sense. Right. So let's say a simple idea, very simple idea. So what if we take an entire model, right, billions and billions of parameters, and we look at basically all the bias terms, right? You have all these neurons, and we are not changing anything there. We are changing only the bias terms, right? Which will basically impact the way the neurons get activated. So some value has been learnt, stored there, but whether it is going to activate or not, that's going to get determined by bias as well, right? It's not interacting with anything else. So just the bias terms. How effective do you think this approach is going to be? Oh yeah, right.
Computationally it will be cheap because gradients are easier.
It's like one of the cheapest things you can think about, right? You do not need to store the gradients for anything, like literally you just have the bias terms, right? It's like and everything else is frozen, right? So this is one of the cheapest and simplest thing you can do, and turns out that's a pretty good idea. So this is basically bit fit. So that's bias term fine tuning, and that's literally the abstract of the paper. And if you look at all these numbers, so that's full fine tuning and weight fit. And if you look at the percentage of parameter that is being fine tuned, that's literally typically less than 0.1%. You're fine tuning less than 0.1% of the trainable parameters. And if you look at the performance, not too bad. It is fairly close, almost everywhere, and in some cases is actually better than full fine tuning. Right. So you might ask why that could be. That is a deeper question we might go into at the end of this talk. But this is pretty fantastic, right? And
This requires full access to the model.
all of fine tuning always requires full access to the model, right? So there are some versions which are none of which is mainstream yet. You can kind of train a model without having full access to it, but somebody still has to allow your updates to go through, right? So now let's think about something that is more on the more complex side. Let's say you have your entire model, and each of these layers that you have, you cannot afford to completely fine tune all of it, right? Because then that is full fine tuning. But what if instead of just fine tuning the last few layers, we add a new trainable layer at each of those layers, in the middle of each of those layers, right? You have, let's say you have something like convolution, then max pooling, and then whatnot, right? In the middle of all that, somewhere you keep adding very small tunable layers, and keep them really, really small in size, and then fine tune that up. Is that going to work? I mean, as you can guess, the answer is yes, and it is in fact one of the leading approaches right now. That is adapters, right? So lots of variation on the ideas, lots of variation on this kind of architectures also. But if you, so this is for example how to do adaptation with transformers, right? Within the transformer block, you are injecting a small adapter layer everywhere, right? And these are like really, really small, and the amount of compute that is necessary to train them up is also very less. And right, and then you train them up, and this works out pretty well in practice, right? So this actually works out pretty great, but the only problem with that is that you're injecting these layers sequentially, right? So it adds to the inference time of the model. So you have a base model which is taking some amount of time to do an inference, and then you adapt it to a new task. It's going to take a slightly longer time to do the inference. I mean, still pretty great in practice, so that's pretty great. And here is another slightly complex idea, but it is simple in the sense that it's parsimonious. It takes only it fine tunes only the parameters that it needs to tune. So it is very parsimonious in that sense. And this is of course LoRA. So freeze the pre-trained model weights and inject trainable rank decomposition matrices into each layer of the transformer architecture. Does that sentence make sense to anyone here, or it doesn't, right? So we will do a deeper. So I'm going to delay explaining that a bit further down the line when I have talked about LoRA a bit further. All right. So let's.
When you add new things, won't it create problems for the old data, and then you have trained on previous data, right? So
No, it will create a problem only if you are still fine tuning the old data, right?
will the accuracy on the
Old task.
old task or old data, like the original data, go down?
Right. So here's the thing. We talked about three different approaches, right? Everywhere we are changing some part of the network additively. You simply subtract that part of it out, you get the original model back, right? So you can recover your original model that way. Secondly, that is something that all of those papers care about. So they demonstrate that you do not catastrophically forget the things that you learnt, because they are designed that way, like they are localized, they are isolated. So it ensures that the things that have been learnt,
We are only improving on whatever.
they are mostly improving. Right, in some cases they do better than the full fine tuning also, right? So it's a lot of wins everywhere. Right. So the idea is this. So if you So I'm going to pretend that this is the entire network. We'll have a better images down the line, but let's pretend for a second that this is the entire network. And if you remember our earlier iteration, we got the data in, and then we get two things, right? We have the weights, network weights, and network weight updates, and we combine them to get the network for the next round. Right. So now, so what if the updates that we have to apply, we split them into two parts, and somehow we identify the part of the update that we are going to fine tune. We find exactly the part that we have to fine tune, and it is very small in size. As we talked about the models earlier, right, it's a vast collection of general knowledge, right? A lot of concepts are there. So we only find 5 or 10 or 20 different ideas that we want to fine tune on, and we simply are able to train those parts of the model. Right. So that's what LoRA is about. So it positions its key insight as the LoRa hypothesis, and as they figured out through their experiments, the hypothesis seems to hold. And what is the hypothesis? So the hypothesis is that the change in weights during model adaptation has a low intrinsic rank. We'll look at these words later on, but what it means is that when you look at an entire model that has been trained, you will often find that there is a very small subset of that model which does equally well. So if you have heard about the lottery hypothesis, has anybody heard about the lottery hypothesis? No. Okay, so I'm going to skip that one and keep to this one. So which is that you have a large model, right? End of the day, this is an optimization problem, and there is a number of parameters that represents this optimization problem, right? So how do you calculate the number of dimensions of this network? You simply look at the number of trainable parameters, right? You look at how many parameters are being introduced at each layer, add them up. That's the total number of trainable parameters that you get, and that is the dimension of your problem. You have to typically train 1 billion, 175 billion, 3 billion parameters. That is the size of your dimension. And when you train the model on your data, on your task, and it is doing very well, so people have been able to demonstrate that that large model of 175 billion dimensions of trainable parameters, it will have a much smaller model inside it, which has much less dimensionality. Let's say something that is of the size 7 billion or 13 billion or 15 billion, which will do almost equally well as the original fully trained model, right? So that's what intrinsic dimension is about, right? There were hello 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 right. So which have demonstrated that in practice. Then there is also the lottery hypothesis that you can look up. So what the authors of the LoRa paper did, so they extended that to the specific architecture of the model itself. So it's not just, so they're hypothesizing that it's not just the entire model which has a equally performant smaller model inside. They are saying each of these layers, the weight matrix of each of these layers, when you are updating them, the update itself also has a small low rank, right? Rank here is, if you understand the dimension, it essentially is the same conceptual equivalence when you talk about the weight update matrices. We will again go deeper into it. I just wanted to introduce the entire flow once before we go deeper. Right. So, right. So, interesting dimension that we already looked at. So, what is the rank of a matrix that we are talking about here? So, this is a 5 cross 5 matrix. Right. This one is entirely 0. This does not add any information to the matrix. Right. So, we look at the number of columns or equivalently rows in that matrix. That's the nullity. You take that away, you get the rank of the matrix. So, in a very loose sense of speaking, this is kind of the amount of information, amount of useful information that you have inside this matrix. All right. So, that is the rank of the matrix. And why do we care about this? Like, okay, maybe you have a large weight update matrix, maybe it has a low rank version. But why do we care about that? Because nullity, as you can see, those are essentially rows of a lot of zeros, right? So, we will be able to decompose this matrix into very small sizes, and all of our operations will become very, very fast, A, and the number of trainable parameters will also go down a lot. So, you need a lot less data and a lot less compute to do your operations. So, let's revisit. Yes.
Null rows or null columns, how are you looking at?
No, so this is a square matrix, so they will basically be the same. So you can also find a null row here, right? They're equivalent. Right. So revisiting that diagram about fine tuning, right? So in this step, we have W prime, and we want to figure out what the update to W prime is in this step. And what we are hypothesizing is that during fine tuning, where we will be computing this from that, the update is low rank. It's a low rank matrix, so that we don't have to do the full computation. We can get away with doing partial computation by targeting the parameters that we care about, the ones that capture that small amount of information in that low rank matrix. Right, so that's why we care about low rank. Computations are faster. This implies that we can isolate and train only the low rank matrix. We will briefly see, soon see how to do that. And the high rank component, the part that you are freezing, so you can think of that as the general knowledge, and the low rank matrix, the update that you are training as the specialized knowledge that go into it. So at each iteration, you have the general knowledge, and you are fine tuning the special knowledge that has to go into it to do your task specific fine tuning. Right. So, and we get all the good properties that we talked about earlier. Right. So now let me look up the time to ensure that I'm on time. Right. Okay. Right. So this we already talked about. Right. I'm not going to go into the exact mathematical definition, but you understand this. So if by transforming the matrix through various linear transformations, if you cannot arrive at rows and ranks that, okay, sorry, my bad, I'm not going to go that route. We'll go back to that simpler version above, which is that it's roughly speaking, very loosely speaking, the amount of information that you have inside that matrix. That's the rank. So what is a low rank matrix? What does it look like, right? So you have your full matrix A, that is M cross N, right? And we call it a low rank matrix if the rank of the matrix is very, very less compared to M or N. You have a lot of rows and you have a lot of columns, but most of them are basically null rows or null columns, right? They don't have any information, any useful information to add. So if that matrix can be transformed in such a way that you could demonstrate that it has a small rank of k, where k is really small compared to m and n. And how small? Typically orders of magnitude. So then we call it a low rank, right? And if it is a low rank matrix, so it will have a factorization of this form, right, where you basically have dimensions m cross k, k cross n, where k is the rank of the matrix, right? If A has rank 5, then you will be able to find an exact factorization like this, where k is 5. So m cross 5 and 5 cross n, which basically looks like that. And everywhere you had to use A, you can replace that with E and F. Why is this interesting to us? Because A has m and n. The number of elements that A has is m into n, and m and n are orders of magnitude larger than k. So if you look at this factorization, for everywhere that we are using A for any kind of matrix operation, we can replace that with this. And E and F taken together, they have k multiplied by m plus n parameters, and that is, if m and n are orders of magnitude larger than k, then this number is orders of magnitude smaller than m cross n. So that is a lot less parameter to train, right? And you can guess where that is leading to, right? And so high rank, basically where the rank is almost as high as it could be. So that's what we call a high rank matrix, but I'm going to skip this one in the interest of time, right? So earlier we talked about A and decomposing it into E and F, right? So how do we know that we will be able to come up with E and F, right? That's what matrix decomposition is about. So these are a class of algorithms with which we can take a given matrix and express it as a product of two or more matrices, which we call matrix factors, where these two or more matrices that we came up with, they have some nice property. Sometimes they are upper triangular, sometimes they are lower triangular, sometimes they are completely diagonal, right? A lot of nice properties which lets us do meaningful things with them, right? And so we are going to specifically look at a singular value decomposition right now, which is how we come up with that whole low rank thingy. And there are guarantees. If your matrix is a low rank one, we have mathematical theorems which will guarantee that you will be able to come up with the necessary decomposition, right? So which is what we do with singular value decomposition. So I'll just go with that quickly. So what singular value decomposition does is that you have your given matrix of some size n cross d. It will express that, the algorithm takes this matrix out and spits out three different matrices, U, S and V, and A is basically the product of US and V, where US and V have some really nice properties, which is that first of all, these are m cross n, d cross d, so these two are square, and S is a diagonal matrix, and all the elements that you have in the diagonal, they are sorted in the descending order by value, right? This is how we do PCA, right? So this is how we get all those principal components from a decomposition like this. So basically you can specify what the ignore the k for the moment. You can specify what you want D to be. Right, sorry, not D to B. So whatever the rank is, you can get the corresponding decomposition. So what we do, we don't want to just do the singular value decomposition and use it. We believe this is a low rank matrix, right? So we truncate this into a low rank factorization. I will cover that in a moment. And if we have a good guess for the value of k, then we have got the right decomposition and our training will work well, right? And this is usually not very sensitive to the value of low rank, because if you got your guess a little bit of wrong, it's not as if things are going to blow up. You'll get slightly worse results. So you would have to figure out what the ideal value of k should be, of low rank k should be, but that's not. I mean, we have guesses for what good values look like. Anyway, you have this full decomposition. So all you do is, from the first matrix, you drop everything so that it becomes n cross k. From this diagonal, you drop everything so that it becomes k cross k. And from this one, you drop everything so that it becomes k by d. Right. So that is truncation. You have the full matrix in the full decomposition, and then you drop all the parts beyond k that you don't want. Right. So why does this make sense intuitively? The way we think about this is like this. These are called the singular values, right? All these values in the diagonal, they are called the singular values. And these are the left singular values, left singular vectors, right singular vectors, right? So those are like your concepts that you have in your, those vectors represent concepts that you have inside your model. And this is essentially how strong or how weak the signal is for those signals. Alright, so what you are doing is you are truncating the signals. You are dropping out most of those things to focus only on a few things. Right, so you do that truncation, you get a truncated version, and that is the low rank approximation with truncated SVD. Right, you do truncation, and that's what you get. And here the k is spectacularly low compared to m and n, your original weight update matrix, if you think about that, which is of the same dimension as the entire network, the entire layer weights. This is fairly small compared to that. So now it makes more sense, the same diagram. So if you remember earlier, we had network weights, and then we added that with the updates, and that was our new updated network weights for the next round, right? So the hypothesis, okay. I think I got dropped somewhere, right? So the low rank hypothesis is that we don't have to train the whole thing, we have to train only the update, and that update we can decompose it as a low rank matrix and simply train that, right? So that update, now it was really large in size, but we don't need to train all of it, right? So we are decomposing that as the multiplication of two very small matrices. A lot of not a lot of operations that are needed to fine tune that. And secondly, we are also truncating from that conceptual point of view. We are dropping a lot of the concepts to focus on a few concepts that we are going to fine tune, or hopefully our training regime will do that for us. Right, so that is the architecture, and the rest of it is there in the paper if you look up. So basically you have A and B. This is initialized with 0 values. This with a Gaussian distribution, and optimization with Adam. And so they do it, and as it turns out, they got all the benefits that they were expecting. For really large transformers, if you just do the calculation by hand, because you are not storing a lot of details about the frozen parameters, the virtual RAM usage, is so they're saving 2/3 of that. When they were basically training on GPT-3, they got the consumption down from 1.2 TB to 350 GB. So that's a sizable, that's the 2 by 3 that they're talking about. So that's a sizable reduction. And more importantly, the checkpoint size is now reduced by roughly 10,000x. Right? It was 350 GB, they got it down to 35 MB. Right? So this is fairly spectacular. And the thing is that for different tasks, you now do not need to train everything from scratch. You do not need to store many different checkpoints. You simply fine tune a LoRa model patch, checkpoint, whatever you call it. And at runtime, you simply load this up, right? And this is literally additive. The original weights are frozen and you're adding this update component to it, right? Sorry. So you're fine tuning this part and you simply load it up, and loading it up is just adding it to the original layer. You want to load a new model, you simply take this out and take the updates for the different tasks and you add that up. So what does it look like in practice? So these are all numbers from the paper, right? Look at the trainable parameters, right? So bit fit was 14.2 mil, and LoRa is basically two different variations, right? One second, missing something there, but the description is not here. All right, but so LoRa will typically so there will be differences in sizes, because also that is also true for the bitfit paper and the LoRa paper, which is that they experiment around which subset of these parameters should be trainable, right? I mean, you look at a transformer model, so there are like a lot of different layers. So the LoRa, finally, I think the results on the paper itself, they are fine tuning the cross attention layer, I think. Not entirely sure about it. Bitfit similarly, so those numbers would be interesting to look at. They talk about the different subsets, like you don't fine tune all the biases in the model. They look at different subsets and see if that produces similar improvement. Right, so number of trainable parameters, as you can see, orders of magnitude smaller, but you actually get better performance than full fine tuning here. All right. Sorry?
The adapter models, those are the PEFT models that you had shown earlier.
So, PEFT has a bunch of things, including, I think, adapters.
So, is this that model?
No, so these are, so when they do these experiments, I think they are quoting from the papers.
Okay.
Like
I don't know, like the adapter model, what techniques is used?
Adapter, so that, right, so that we had talked about earlier. So in adapter models, what you do is you inject a trainable layer into its.
It's using that model.
Yeah.
Okay.
Yeah. Where do the numbers come from? They did not train their own version of. They got the numbers from the paper.
LoRa, they've experimented with different rank values, like the K values. Do you experiment with that?
Yes.
It's like a hyperparameter.
Yes. So the low rank, that is K, you are hypothesizing that there's a low rank which captures most of the value here. So they experimented around it. I don't think I have included a graph. No, I have not. But basically K, so they got really good performance for K equal to 4.
Okay.
So as in, like, if I had no further information and I had to train a model like this, I will go with K equal to 4.
What could it potentially depend on, the K value? Like, does it depend on like the original model size, or like it works throughout?
So technically speaking, it captures the complexity that is there in your fine tuning data, right? If you have a really large amount of fine tuning data about a diverse set of
Maybe a larger
things,
K would.
then you would need to go for larger K. You have multiple languages inside your data set. I mean, like whatever use case you can come up with. So K would have to be fine tuned for your specific data set, for your specific task, and 4 is a good starting point, I would say. So K equal to 1, 2, they're kind of bad performance. Performance kind of starts to saturate around 3, 4. So,
But it seems like fine tuning data quality is like really important. So like,
I mean, that is true for everything. Pretty much, it's garbage in, garbage out. Though it, with large language models, you never know. Little bit of garbage can be helpful. So
the ones that you like Wiki SQL and these ones, how large are they?
that I would have to. So
Or in general, I'm just wondering, ki, like for LoRa, like how many data points would you say, ki, like the dog example that you gave?
yeah. No, so typically when you look at these kind of numbers, so they make sure that they take they have some diversity in the data sets that they evaluate. I don't remember offhand the specific thing about YKSQL because I've not really worked with that. I remember from the BitFit paper, they had taken two data sets. They ensured that one had like 3.5K and one had 360K plus data points. So they go for diversity. So usually they take care of that.
And I suppose when they are doing this computation, they would ensure ki the original training data would not contain these data sets. As in, like if it is already part of, like before fine tuning, you have already trained on it, then you're like cheating, right, when you're fine tuning on it again.
Right. No, so they might have seen this data set, but they are not trained on these tasks that they're trying to optimize it for, the specific task that you're looking at here. So they might have seen it. So which is why, so this one went for GPT-3 and they could demonstrate an improvement in performance even on top of GPT-3. But you look at most of these papers, they typically take something like BERT, etc.
What was the specific task they were fine tuning for?
So I don't remember if this is binary or not. YKSQL has that for each of these I would have to like look up. I don't remember offhand. Right, so, right, any further questions? Yes. That one I think is not working.
I'll try.
So, as usual, always listening to your talks stretches my mind to the limit. But I think I got most of it what you said. I have 2 points. One is, as you said, that this is an optimization problem. Right? Ultimately, you are getting into matrices and you are getting into number of parameters which are number of dimensions and all that. And traditionally with optimization problem, there is a duality in topology. Is there any research around that, whether there is a dual topological problem statement for this?
That is not something I have. I mean, I keep seeing people talking about stuff like that, but I mean, given the large parameter space, you level everything in GPT-2, so that's a good exercise. But I think what you are saying, for that we have to reach a place where GPT-3 is able to self-annotate itself and expose everything about itself.
It's literally impossible possible.
Right. No. So I mean that's a hard place to be, but I think we need a few further theoretical breakthroughs before we can get to a place like that. And a lot of these things will be outdated by the time we get there. So yeah, a lot of this will be outdated.
So for the time being, this is good enough and we should.
Yeah, so this is a fairly, so I think this is the right direction. I mean, so one good thing about LoRa that I was going to mention, okay, this is a deeper dive, but right, so one good thing about it, LoRa is, for example, is that it plays nice with others. All right, so a lot of other, all these prefix tuning, you have adapters, you have BitFit, etc., right? A lot of them work together nicely, right? So because you are keeping all that isolation, localization is now basically is going to pay off, right? And you can combine these things together, right? I mean, this model is fine tuning in this locality, that model in that locality. So I think we will probably get more variations on the same theme, and Right. So basically take a look at Unipelt. Uh, that basically does the for language models that lets you combine a lot of different approaches and play with them. So LoRa is going to be
Thank you.
useful there. Okay. Yes.
So, do any of these techniques also apply to fine-tuning embeddings models, or is it different because that's involved?
What is an embedding model?
I mean, something like S-word or
No. What I'm saying is that what is an embedding model? It's not a different class of models, right?
Yeah, it's the first part of it basically. You can think of.
I mean, yeah. So it's a regular model like any of these things. If it uses a transformer somewhere, you will be able to take a lot of these techniques and apply it there. And even models of other kind, you can take these techniques and apply them there. So being an embedding model has nothing to do with any of these
But
things.
I guess the size of those models is currently small enough that people are able to do.
No, there's nothing about embedding models which dictates that they have to be small or large.
No, I mean the current state of the art, like E5 or.
No, they are small models that those companies have open sourced, right? But if you used any embedding service provider, those models are typically fairly large.
Okay.
And even a BERT model, if I had to, I mean, this will not be a realistic use case because I'm not going to be a service provider. I'm most likely going to take SBERT and use it for some specific use case. And I'll have probably a single data set, I'll fine tune on it. And even there, these things are still worth a try because as you could see, so there is one more thing that I didn't talk about, which is that a lot of these tasks will have a commonality, right? And sometimes you want your fine tuning, your parameter efficient fine tuning procedure, you want it to improve the overall performance also, and that happens quite a bit if you look across papers, across numbers, to the extent that we can trust them. Though, I mean, these things have been quite been replicated in practice, so that is good. So you'll see that the performance goes up. So as an individual, that's not necessarily very important to me, right? One data set, and probably if I can afford the infra, so that is fine. But think about it 1 year down the line, I'm pretty sure you wouldn't really be able to train things without this kind of techniques. Think about all the generative AI artists that are building things today. Most of them would not have been able to make the kind of progress that they have made without something like LoRa. The compute requirement, etc., would be like way more, right? And you expect to make mistakes, and every mistake is fairly expensive, both in terms of time and money and infra, right? So this allows things to move very, very fast, and that's like half the reason why we see so many movements today. Right. But coming to the second part, of course, I mean, if you are providing it as a service provider and you need to fine tune it across different kind of domains, then you would need to use something like this, right?
Could you tell us about some use cases where LoRa fine-tuning would not help versus where it would be, like you said?
Sorry, you're not very audible.
Talk about some use cases where LoRa fine-tuning would be a good idea versus not a good idea, like those use cases where it would not help.
Right. So, I mean, so I don't think we are fine-tuning ResNets a lot anymore. I mean, if you have to fine-tune ResNet 18, so that's where this will not be very useful. And that's if I want to be black and white, that's pretty much the only place I could say this. But almost everywhere else you would want to use LoRa, as in particularly in the generative AI space, whether it is in vision or NLP, you typically will want to use LoRa or some variation of the idea. Full fine-tuning is simply not good enough. It's not just about the performance and the compute. It's also about data, and I think which is a critical bottleneck right now. We just don't have enough data. So we want techniques which can extract all the juice that we have in our data. So, instead of training billions of parameters where you don't know which ones, where should your updates be, go with something like this which can selectively fine-tune your model and get the max amount of information out of your training data. Yeah.
Hello, hi.
Hi.
So one of the things, like foundational part of how LoRa works is that the weight matrix can be decomposed into low rank matrix while preserving the.
So not the weight matrix, the update to the weight matrix, that can be decomposed into low rank matrix. There is no reason to believe that the weight matrix itself can be low rank because it comprises of a really large number of concepts, right? But the update that we are creating for it, that can be decomposed into low rank matrices. So the update itself consists of very few concepts, right? Like, so, yeah.
Okay, then my question is.
Okay. Still, I would like to.
So I was just thinking that, does it mean that automatically the model can be distilled into the, if the weight matrix itself can be.
Right. I mean, wouldn't feel of that, but that's not how it is.
Hi, great talk first of all.
Thank you.
For someone trying to implement this at production level, right? Let's say I'm a customer support chatbot company, right? I have that kind of data set available. I have that kind of compute available, right? How do I, go about that process of, what kind of fine-tuning technique is best suited for my use case, and probably, how does that decision making go forward from there in terms of what model to choose, what technique to choose? If you could just list out the considerations in your mind, right, that would be helpful.
Right. So I don't know how your application is organized, right? But we have different use cases, right? So typically you will be fine tuning some kind of model, right? Either for generating embeddings or generating text, right? So whatever the model, whatever the task is. So I would suggest go ahead with Unipelt. So I mean, each of these things have kind of reduced the amount of effort you have to make to a very minimum. So just go through the official pages, transform. Yeah, so all the techniques that I talked about here and other techniques, a lot of them are covered and they're like one line of code away. So just ensure that pay attention to your data basically. All right, so I had to choose between doing a more theoretical version and a hands-on version. So I went ahead with the theoretical one. So I will be, so I'm going to put out a small booklet on this on Twitter. So that's one motivation for you to follow me on Twitter. So if I come up with that, so that's Data Biryani. So you can follow me. So I hope to put that out sometime within the next week or two. And so I'll cover the practical aspects there too. But honestly, just go and look at the documentation. It's fairly straightforward and very, very easy.
Any questions? Last question.
Like the trend I've noticed in language models at least is like really eliminate fine tuning and bring everything to the main training loop itself. As in like earlier, like natural language understanding had a separate task, question answering was a separate task. Today, all of it is like combined into just generation. Similarly, I guess I don't know if images have the same thing, but like I am sensing ki like in future, like big companies would prefer not having fine tuning and just making the training loop itself contain as much data and as many tasks as possible. So, like, do you see like fine tuning playing a big role in future?
So slightly different questions. So let me rephrase what you said. It didn't really happen that way. Nobody in his right mind cares about POS tagging, part of speech tagging, right? I mean, what do I care about that, right? A lot of different kind of tasks existed because I wanted to do something meaningful at the end of it. I want to classify sentences. That's meaningful. That's something I care about, right? It turns out I can use parts of speech like how many nouns, what kind of nouns, what adverbs are there. I can use them as a feature to do a good job at classification. So we cared about that. And a bunch of algorithms got developed for part of speech tagging, right? And tons of other stuff that that we used to have, right? So it turns out, I would also like to observe that when we did those things, we actually created a representation for the data, right? And those different representations, they became features in the final thing that we wanted to do. So as it turns out, I can simply feed all of my data to a really large network, and it will figure out those representations, and I don't have to care about it, right? So at that moment, we stopped caring about all of those tons of different tasks that we cared about in NLP. I'll not say they're completely dead yet, but a lot of them have certainly become redundant. So, right. So that happened, but the different kind of tasks that we care about, those will still be there. So fine tuning will be relevant for a long time, and given the situation that we have with data, we have a lot of data, the copyright and IP of which is not entirely clear. I think there will be maybe slow, maybe a fast one, I don't know. Most likely a slow one. There will be a shift towards building foundational models which can do reasoning better, which can do composing better, and then we will take them and mostly fine tune them with our own data set, right? So I think fine tuning is going to be fairly central to that whole approach, I would say.
Thank you, Soumendra. This is great talk actually.
Thank you.
Really, I think we have a lot of great questions also. So thank you everyone, and thank you to actually one round of applause to our speakers. I think our